Hello friends, in this video I'd like to solve the following problem from Concrete Mathematics textbook, problem 37 from chapter 6. We wish to express the following sum from k equals 1 to m times n of k modulo m over k times k plus 1 in terms of harmonic numbers, assuming that m and n are positive integers. And finally, we wish to find the limiting value as n goes to infinity. M is fixed, n goes to infinity. So here are my hints for this problem. First, recall that nth harmonic number is by definition sum of 1 over k from k equals 1 to n. Then you can notice that we have some kind of denominator in our sum. Use partial fraction decomposition on this denominator, on this entire fraction, to split it into two fractions and then try to shift the index of summation to make fractions with the same denominator. Again, also, the following value, k modulo m minus k minus 1 modulo m, you should be able to find the explicit value of this difference of remainders. And finally, for the last part of our problem, we recall that, or it's a well-known fact from mathematical analysis, that limit as n goes to infinity of nth harmonic number minus natural log of n equals gamma, where gamma is famous Euler-Mascheroni constant. We'll give this problem a try and I will see you in a minute. Okay, so here is my solution. First, let's notice that 1 over k plus 1, it's just 1 over k minus 1 over k plus 1. It's the partial fraction decomposition of this fraction. And that allows us to write our sum going from k equals 1 to mn, k modulo m over k plus 1, we can split our sum into two different sums. First is from 1 to mn, k modulo m over k, minus the second one, sum going from k equals 1 m times n, well, k modulo m over k plus 1 this time. Okay. And now, I wish to do the following things. First sum will stay the same for now. K modulo m over k. And for the second sum, notice the following things. I can start my summation not from 1, but from 0. Why is that? Well, if I add k equals 0, we know that k modulo m, 0 modulo m is just 0. So we are just adding a 0 term into our sum. And moreover, let's notice that we can end the summation on mn minus 1 instead of mn. Again, why is that? Well, it's that because if k equals mn, we have a multiple of m. And again, mn modulo m is 0. So we can omit these two terms. And now, the first sum will stay as it is. But for the second sum, I wish to shift the index of summation. Instead of k, I will put k minus 1. Maybe write it in red. I wish to put k minus 1. So k minus 1 goes from 0 to mn minus 1. Well, instead of k, I have k minus 1. And here in the denominator, I will have k minus 1. Modulo m minus 1 plus 1. Very well. And now, let's notice the following. The first sum stays as it is. And the second sum, well, if k minus 1 is 0, k equals 1. If k minus 1 equals mn minus 1, k equals mn. And here we have k minus 1 modulo m over k. And after all of that, we can combine these two sums again into one sum. In the numerator, we have k modulo m minus k minus 1 modulo m all over k. Very well. Now, let's take a slight detour and find the value of the numerator. K modulo m minus k minus 1 modulo m. What is it? Well, I claim that it's either one of two things. First, if k is a multiple of m, what then? Well, if k is a multiple of m, then the first remainder is just 0. It's just 0. So we have minus m minus 1 in the result. But if k is not a multiple of m, then here we have something, r, and here we have r minus 1. r minus 1. So r minus 1, it's just 1. So our remainder is one of these two things. Oh, sorry. And that is very helpful, because now we know that our sum can be split again into two different sums. One sum will be over k's which are not multiple of m. Maybe let's write it in orange. Well, if m doesn't divide k, in the numerator we have 1 over k, 1 over k. And then we have our second sum over all multiples of m. And then in the numerator we have minus m minus 1 over k. Very well. And what now? Well, the first sum will stay as it is. One over k. And I will split the second sum. I will have minus m sum from k equals 1 to mn over all multiples of k, 1 over k. And finally, minus minus is plus. Plus sum going from 1 to mn. m is dividing k, 1 over k. And what now? Well, now, again, one simple manipulation. Notice that this sum and this sum, it's again just sum from k equals 1 to mn. Why is that? Well, because either m divides k or m does not divide k. Both cases are covered by one of these two sums. So these green sums can be combined again into sum going from k equals 1 to mn, 1 over k. It's these two green sums can be written as that, and minus m. And now let's notice the following. Here I will, you know what, I will omit sigma notation. We are summing from k equals 1 to mn over all multiples of m. So we are summing 1 over m, 1 over 2m, 1 over 3m, and so on. Finally, 1 over n times n. And now, what is the first sum? Well, we are summing reciprocals of natural numbers from 1 to mn. So this green sum, it's just harmonic number with index m times n. And what about this part? Well, it can be written as minus 1 plus 1/2 plus 1/3 plus 1 over n. And what is that? Well, it's just nth harmonic number. So it's HMN minus HN. And that is our result. Our entire sum can be written, so our sum going from k equals 1 m times n, k modulo m over k plus 1 can be simplified quite a bit as HMN minus HN. And that is our result. That closes the first part of our problem. But the second part is quite easy, because now we want to find the limiting value as n goes to infinity. So now we just take limit as n goes to infinity of HMN minus HN. And now, the tricky part, somehow tricky, I will write in this special form. I will introduce, first I will subtract natural log of m times n, parentheses is not necessary. I will have minus hn, and I will subtract or add this time natural log of n, but I can't just simply subtract some natural log and add something else. Now I'll have to add the missing terms, but I don't have space, so okay, minus my natural log of mn, or rather plus, minus natural log of n. Now everything is all right. And now, if you recall my hint from the beginning of my video, well, this goes to Euler-Mascheroni constant, and this combined with minus, it goes to minus Euler-Mascheroni constant. So it's gamma minus gamma. And what's the last part? Well, by well-known properties of natural log, or any log for that matter, natural log of mn minus natural log of n, this part, it's just natural log mn over n, which is natural log of m. And remember that we are taking n to infinity, not m. So it's a constant. Plus natural log of m, and that simplifies, and we have our result. Our limit, it's natural log m. So maybe let's write our answer right here, and let's close this problem. Yes, and that's it. So our sum can be simplified as the following difference of harmonic numbers, and our limit equals natural log of m. Natural log appeared. Yes, pretty nice problem, I say. Lots of sigma manipulations. To be honest, one more word before you go. This constant, this Euler-Mascheroni constant, denoted usually by gamma, it's a very curious constant. To this day, it's not known if it's rational or irrational. So it's still an open problem in mathematics. It makes it interesting. It appears also in many integrals, sums, series, and so on, limits. So yes, thank you for watching, and I will see you next time. Goodbye.